Advanced Algebra 2 students, welcome to your 9.4 notes. Today we're going to take a look at ellipses. I will tell you that some of the numbering's a little funny on these notes. You may catch some other little glitches because I adapted these from a previous course and it's just fine. They'll work perfectly for you. So let's start with the definition. An ellipse is the locus of points x, y in a plane, the sum of whose distances from two distinct points, foci, is constant. Now you can see the diagram here to the left. I actually want to show you though on something called Geometer's Sketchpad. I'm going to show you kind of a visual of this. You can see if we had a string connected to 2 points and we drag that pencil around, you can kind of see what that looks like. Kind of cool stuff. Now I'm going to come back to that in just a moment, and we're going to look at that again for a couple of other things. Some terminology we need to know. The major axis is the distance between vertices. The minor axis is the shorter of the two axes. And I should probably point this out. On either side, we don't have these labeled, but at times you'll see these 2 points called co-vertices. So if you ever see the term co-vertices, it's referencing the ends of the minor axis. It's kind of like a squished circle, right? So it's kind of like the shorter radius, the shortest radius is the end of those is where the co-vertices would lie. The center, I think, is self-explanatory. All right, this diagram over here has a lot going on, but the main thing we're trying to point out here is the relationship between A, B, and C. A represents half the major axis. B represents half the minor axis. I think of it as the largest radius and the smallest radius, although I'm misusing those terms a bit. And C represents the distance from the center to the focus point. Now you can see there's a whole bunch of stuff going on here, and you've got some formulas, but let me show you a way that we can think about this that might help you to understand it. The first thing you need to understand is that the string that we're dragging around to create the ellipse has a length of 2a, and you can kind of see it visually if we drag the pencil down to here. You can see that this gap from the focus point to the vertex is actually doubled up, which makes up for that gap right there. So the string has a length of 2a, okay? But now, here's the really cool part. The relationship, since we know the string is 2a, we know this hypotenuse of this triangle right here has to be a, that's half the string. We already defined this as b, the distance from center to a co-vertice. And then C is the center to the focus. So we've got this Pythagorean theorem situation, except, well, it's Pythagorean, but it's a little demented. You can see it here, a squared equals b squared plus c squared. You might also see it written as a squared minus b squared equals c squared. Honestly, any of those are fine. Use what you're comfortable with, and it makes sense. Just make sure you don't accidentally use the real Pythagorean theorem. I mean, we are using Pythagorean, but we have the sides labeled differently, all right? And when we get to hyperbolas, we actually have a little bit different format on those, so we have to stick with this one here. All right, the standard equation, you can see the 2 forms. The first is when you have a horizontal major axis. This is like if you had a circle and you squished it from the top and bottom, so it's wider than it is tall. This second version is a vertical major axis, and that one would be, again, like if you took a circle and then you squeezed it from the sides, kind of squished it, so therefore it's actually taller than it is wide. Now, these two standard forms look very, very similar. There's only, as you can see, one difference. It's the location of A and B. So the point is, if the major axis is 2a, then that means the distance, again, from the center to a vertex is a, and that is always bigger than the distance from the center to a co-vertex. So the point is, if it's horizontal, the bigger number is under x. If it's vertical, the bigger number would be under y. And we'll take a look at that as we move forward. Hey, one more thing we want to talk about. It's a new term for you, eccentricity. We're going to really focus on this. We'll hit it more second semester too, when we go a little more in depth with some of these figures. But eccentricity is defined as C over A. We can use eccentricity to figure out at times what shape are we talking about, but also we can tell, you know, a little more detail about the shapes. We'll get into that later. All right, let's get right into it here. So we're going to, for the next couple of problems, identify the conic as either a circle or ellipse, and then we need to find all the key information, and we'll go ahead and sketch that graph while we're at it. All right, so first thing I want to know, if I want to know if it's a circle or ellipse, that's actually pretty easy. Those two numbers right there tell the story. This is most definitely an ellipse. If it was a circle, those two numbers would be the same. All right, so let's talk about what we know. I know that this term right here has to be a squared, so that means that a is going to equal 10. This term right here, 36, has to be b squared. And again, the only reason I know which one is a and which one is b is it's based solely on the fact that a is larger than b. So a is 10, b is 6. The center, well, there's no move from the vertex, so we're just at 0, 0. I said the vertex, I meant the origin, of course. And the radius wouldn't apply. We'll deal with foci. We can deal with eccentricity at the end as well. All right, so let's go ahead and sketch this thing. I know the center is, again, at the origin. And when I see this, I look and I'm like, okay, remember, the b value of 6 is horizontal, so that means I need to move 6 spaces right, 6 spaces left. The a value of 10 is a vertical change, so we're going to move up 10 and down 10, and again, in both cases, those are from the center of the shape. And then we're going to go ahead and sketch it. I always find ellipses a little tricky to sketch, so my drawing will not be perfect. That may shock some of you. Not those of you that know me, though. And the thing is, your drawings won't be perfect either, and that's totally fine. You don't have to worry about perfection. We're looking for a nice sketch. All right, we still have a little more work to do. First thing, let's go ahead and list the vertices. We've already graphed them, so that's pretty simple to do. Those were the furthest points from the center, and I'm just going to list them as 0, plus or minus 10. Okay, we also need to find the foci. Well, in order to find the foci, I need to find C. And so remember, we have to use, and I'm going to jump back a slide just to remind you, down here we have to use that alternate version of the Pythagorean theorem. So it's a squared equals b squared plus c squared, or you could just do it as c squared is a squared minus b squared. So that's 100 minus 36, which is 64. That's convenient. C is 8. Okay, one other thing about the foci that we probably mentioned, but we probably wouldn't hurt to highlight that, is the foci are always going to be on the major axis. So I know the foci are at 0 and plus or minus 8. Okay, and then the last thing we need to do is the eccentricity. Remember, eccentricity is C over A. So in this case, that would be 8/10, which of course we could simplify to 4/5. Now, the point of eccentricity, you may be wondering just a little bit, like, what's that even mean? And again, we'll get more in depth with this later in the year, but for now, you can know this. The closer you are to 0, the eccentricity, I should say, is to 0, the closer that ellipse is going to be to a circle. So a circle actually has eccentricity exactly of 0. An ellipse is always between 0 and 1. The closer it is to 1, the more elongated that ellipse would look. The closer it is to 0, the more circular it would look. All right, we have the same instructions on this next one. Let's work on it. Now we do, as you can see probably right away, we have some new things to deal with. For one, we have a center that's moved off the origin. It's at 1 and -3 this time. I probably should point out, I didn't write it or say it, but I noticed right away with a 9 and a 7 here, this is definitely an ellipse. Okay, so we found the center. Radius doesn't apply. We're going to need to find vertices, foci, eccentricity, and sketch the graph. All right, our a squared term is 9, so that means a is equal to 3. Our b squared term is 7. That means b would be the square root of 7. We might as well go ahead and find c. So we know c squared is equal to a squared minus b squared. So c is going to be the square root of 2. Once we've put this information together, honestly, we have enough to be able to start sketching the graph. So I'm going to start by marking the center. It's at 1 and -3. I know that the larger of the two changes, the a value, is horizontal, so I'm going to mark 3 spaces right and 1, 2, 3 spaces left. I know that vertically we're changing by square root of 7. Now, square root of 7 is approximate, of course, but it's between 2 and 3. I'm just going to mark it somewhere in between 2 and 3. We're not going to get too crazy about the precision on marking square root of 7 on an elliptical graph. All right, so I have enough to be able to sort of sketch an ellipse that looks somewhat elliptical. All right, we'll roll with it. Okay, I need to mark some of the key information. Now, here's the thing to remember. The center's at 1, -3. The vertices were to the left and right of that center. Okay, so I don't actually have to write the 2 points out separately. If you'd like to, you could do it like this. The vertices are 1 plus or minus 3, -3. Now, of course, that's the same as saying 4, 3, or 4, -3, excuse me, and -2, -3. You can do it that way too. We haven't talked about where the foci are. I'm going to change colors here so we can see those. They're the square root of 2 away from the center, which square root of 2 is about 1.4, so I'm going to mark those there. The foci are at 1 plus or minus square root of 2 and -3 still. And then lastly, we need to talk about the eccentricity. The eccentricity here, it's always c over a, so in this case that's square root of 2 over 3. Now if we're approximating that value, it's about 0.47. Now my drawing may not be the best way to look at this, but if we sketched this on using technology, or if you were better at drawing the ellipse than I was, you might notice that this one looks somewhat circular. So even at an eccentricity of, we'll call it a half, about a half, we're already getting a little bit closer to looking like we have a circle. All right, same instructions on this one, but this one's going to be pretty fast. You notice that the denominators are both 25. This is a circle, folks. And when it's a circle, we can just start by labeling the center. It's 3, -9, and we know the radius would be 5. All we're really going to have to do at this point is sketch that thing. There's really not much else for us to do. 3, -9, radius is 5. So what I'm going to do is mark the points that are left, right, and above. Now obviously below is going to be a bit of an issue. You could try to approximate if you want, and I'm going to use my little tool so I can draw a circle. It's nice and amazing, just like all my drawings are, except this one's better. Okay, last thing, eccentricity. Well, the eccentricity of any circle, as I mentioned before, is 0. Some clue questions where we're going to work in the opposite direction of what we've been doing. So instead of finding out all the stuff, we're going to find the equation. So we have to think about what do we have to know. So you have to think about the standard form, and if it's vertical, of course, for any ellipse, it's x minus h squared over, well, if it's vertical, this would be a b squared plus y minus k squared over a squared equals 1. Sorry for that handwriting, but you've got it written in your notes already. But when you look at this, basically what I need to know is I need to know the center. So on number 6, that center's at the origin. I need to know A and I need to know B. Well, A is the further distance from the center, so that would be 5. the shorter distance would be 4, and that's the b term. I'm honestly ready to roll here because the center at the origin makes this problem easier, honestly. So x squared, that's the horizontal movement. So this is x squared over 16 plus y squared over 25 equal to 1. It's that simple, kids. All right, here's our next one. Now this one, we have to do, 5% more work because I have to be able to think and I have to understand and not memorize the middle or midpoint formula, but I have to be able to think. So here's what's halfway between -8, 2, and 0, 2. That, of course, is -4 and 2. There's your center. Okay, so if you want to draw it in there, you can, but you've got to think about this in terms of, well, what are my other values? Well, the A value, that's 4 spaces away. That's half the length of the major axis. The B value, well, the minor axis has a length of 6, so that value is 3. Sorry, there we go, 3. And this one's horizontal, so I know the larger value is going to be under H, or excuse me, under X. Let's try that again. All right, so here we go. X plus 4 quantity squared. I'll leave the denominator blank for a minute. This is usually how I do this. Y minus 2 quantity squared over something equals 1. We already talked about it. The A term is connected with the horizontal, so 16 needs to go under X, and the vertical aspect is the B term, so it goes under Y. All right, 4 clue problems left. They all have a little bit different information. Let's take a look at them. Number 8, vertices at 0 plus or minus 6 tells me a couple of things. First, I know that the center would be at the origin. Second, I know the A value is 6. Okay. Oh, one more thing. If the vertices are at 0 and plus or minus 6, I also know that this ellipse has to be vertical. And by vertical, I mean a vertical major axis. Okay, so it's taller than it is wide. Okay, the foci being at 1, 0 plus or minus 1, I should say, tells me the C value. Now, by knowing A and C, and knowing that A squared is equal to B squared plus C squared, I can pretty quickly figure out that B squared is 35. And yeah, you could figure out B if you wanted, but here's the reality. All it says is find the standard form. So if we're being honest, we don't really care that much about B. We care a whole lot about B squared, right? All right, so I just wrote it this way. I included my center. It's at the origin. The only thing I have left to do is plug in the A squared value and the B squared value. Well, this is vertical, we said. A is connected to the Y, so there it is, 36. And then the B value of, or B squared value, I should say, of 35 would be connected to the horizontal part. All right, next one. Again, if you just look at something like knowing the foci, you can figure out a lot. Like, I know right away that if the foci are at 0, 0, and 4, 0, I know the center's at 2, 0. I know that the C value is 2. Also, if it's 0, 0, and 4, 0 for the foci, I know that this ellipse is going to be horizontal. Okay, major axis length of 8, that gives me the A value of 4. And then if we do 4 squared is equal to 2 squared plus B squared, we can pretty quickly figure out that B squared is equal to 12. Hey folks, we're ready to set this thing up. I usually like, again, just to start by marking the center and leaving denominators blank just momentarily, because it's always going to be like that, right? The center is 2, 0, so it's x minus 2 squared plus y squared. Now let's talk about denominators. We said this is horizontal, so the larger value, the A value, should be connected to x. And if A is 4, then this is 16. This is 12. And what we have there, folks, is a lovely standard form ellipse equation. All right, let's do number 10. Again, if you look at vertices, you can figure a lot out. I know the center is going to be at 3, and oh man, this isn't fair. Oh, -6. It's fine. What's halfway between -1 and -11? Add them together, divide by 2 if you need to. All right. Also from that, I can figure out that the A value here would be 5. I can figure out that if the vertices are 3, -1, and 3, -11, that this ellipse would have to be vertical. And then, oh, this is weird information they gave us. Eccentricity is 3/5. Now remember, eccentricity is C over A is equal to 3/5. But we know A is 5, right? So that tells me then that C has to be 3. And, if I know C and I know A, I can just say, well, I know the relationship here, 5 squared is equal to B squared plus 3 squared. So I know B is 4, or maybe more pertinent for our purposes here is that B squared is 16. And you know what we are? We are ready to write our standard form elliptical equation. So x minus 3 squared plus, and then we'll have y plus 6 squared equals 1. Let's fill in those denominators. We know it's vertical, so I'm going to the y value, and I'm going to write a squared underneath it, which is 25. And then I'm going to go to the horizontal part and write b squared. And then I'm going to be done with that problem. I'm going to go to the one you've all been looking for, the last one. All right. Again, let's look vertices and get as much information as we can. We know the center would be at 3 and 5. Also, if it's 3, 8 and 3, 2 for vertices, I know for sure that it's a vertical ellipse. And I mean 3, 8 to 3, 2, that's 6 spaces. That's the major axis, so I know A has to be 3. And then it gives me the co-vertices, although it's calling them endpoints of minor axis at 4, 5, and 2, 5. That's kind of a giveaway to say that my B value is 1. And I like this because I've got A, I've got B, and I've got my center. So here we go, x minus 3 squared over something plus y minus 5 squared over something equals 1. Now again, we said this is vertical based on the location of the vertices, or you could look at it based on the minor axis. And if it's vertical, that means the a values connected to y, so that's a squared, which would be 9, and then b squared would be 1. That, folks, is the end of your 9-2 ellipses notes. I know it's been kind of lengthy today, but there's a lot of good stuff going on here. Make sure you learn the patterns and do well. Have a spectacular day.